Okay, this is section 1.4, part 2. So we last ended with the definition between elements and compounds, okay? And the next part of that is the law of definite proportions. The law of definite proportions reads that a pure compound, whatever its source, always has a definite or constant proportions of elements by mass. So this image here shows you carbon dioxide. And carbon dioxide has some ratio of 12 grams of carbon to 32 grams of oxygen, or 16 times 2. So this is what this one is. If I double the 12 to 24, that means I need to double the 32 to 64. If I multiply the 12 by 3, I get 36. And if I multiply the 32 by 3, I get 96. So this proportion stays constant. So I want to show you a little bit more of this example. Okay, so this is a different example. This is sulfur dioxide with 2 oxygens versus sulfur trioxide with 3 oxygens. So same thing, that for every 32 grams of sulfur, 32 grams of oxygen exist. So this is a 1-to-1 ratio. So 32 divided by 32 and 32 divided by 32 gives me the 1 and 1. So if I have 160 grams of sulfur, how many grams of oxygen should I have? Well, since this is 1-to-1, it's basically going to be 160 grams of oxygen. So this ratio of 160 to 160, or 1-to-1, or 32 to 32, is what's going to identify this as being sulfur dioxide. Versus if I look at sulfur trioxide, where I have the 3 oxygens here, that means that for every 32 grams of sulfur, I have 48 grams of oxygen. So this ratio is different. If I divide by the smallest number, which is 32, so 32 divided by 32 gives me 1, and then 32 divided by 48 gives me 1.5. So you see how this ratio is different than that ratio. So even though the compound is made up of the same elements, the ratio of elements is different, so therefore the ratio of masses of the elements are different. And this is going to help identify whether, if I have a compound and I don't know what it is, but I can measure the relative masses of my elements, which there are procedures to do that, I can tell if the compound in question is that of sulfur dioxide or sulfur trioxide by this ratio. So again, if I have 160 grams of sulfur, how many grams of oxygen do I have? So since the ratio is 1 to 1.5, I'm going to take 160 times the 1.5, which here's me grabbing my calculator. 160 times 1.5, that gives me 240 grams of oxygen, okay? And so, again, it doesn't matter what mass I have, the ratio of those masses will be constant for the 2 elements here in sulfur and oxygen. It doesn't matter. If it has 5 different elements in it, the ratio of the masses of those elements will be constant for a particular compound, okay? Now, so that's compounds. Now we get into mixtures, okay? A mixture is a material that can be separated by physical means. So a compound cannot be separated by physical means, only by chemical changes, whereas a mixture is by physical processes, okay? And then there's 2 divisions of that. There's a heterogeneous, which means there's physically distinct parts, okay? They don't have to be of different states, and we're going to see some examples of that, but they have different properties, and you can see physically what two or more what different types of components of that mixture is, versus a homogeneous mixture, okay? It's uniform. You can't see the different parts of it. So this diagram here shows you a heterogeneous mixture. They're going to this one shows the fact that they're physically separated, but they don't have to be, and I'll show you that in just a second. But you see the fact that you have red balls and green balls, okay? And the fact that there's distinct differences there, okay? A homogeneous mixture, they're mixed in between, and I would kind of rather the fact that they would be just different shades of pink. because you can't see necessarily the fact that they're different balls. Again, I'm going to show you an example of that. So this right here is from the textbook, okay? This is a watch glass that has a mixture of potassium dichromate, which is the orange, like right here, and iron fillings, which is the black, kind of scattered through here, the dark spots, okay? This is one, again, where they're mixed, okay? And they're probably pretty uniformly mixed, but I can definitely detect whether something is orange or whether it's black, okay? Now, simply by putting a magnet over this, because iron is magnetic and the potassium dichromate is not, then the iron will physically come out of this process. I don't have to do a chemical reaction to separate these two things. And so this is a heterogeneous mixture. And it's one in which they can be mixed within each other, but you can still physically see them. And they're of the same state. I can have a heterogeneous mixture of, say, oil and water. Okay, think about Italian dressing. If I shake it up, okay, it's an oil and vinegar mixture usually. If I shake it up, I have bubbles of oil through the other liquid, okay, which is vinegar. And so you can see the physical differences between those two things. So this diagram here, basically matter is anything, remember, that you can sense, okay, can be broken up into two categories. Okay, I have substances, which means that they cannot be broken up by physical processes, and mixtures, which can be broken up into physical mixtures. And then under substances, I have two types. I have elements and I have compounds, and I can go between these two by chemical reactions or chemical changes. And I have mixtures. I can go between substances and mixtures by a physical process. Okay. Which was like the showing of the magnet and the iron. There we go. And then under mixtures, I have either homogeneous, which is also called solutions, so I can't see the difference, and heterogeneous mixtures in which I can physically see the difference. So here's some problems. So the following processes involve a separation of either a mixture into substances or compound into elements. Decide whether each is a physical process or a chemical process or chemical reaction is required. So if I have sodium metal from sodium chloride, okay, so sodium is an element, and sodium chloride is a compound. So therefore, this is a chemical reaction. I keep losing the cursor. So this one is chemical. So when the name is part of, and it tells me here it's a substance. So if it's a substance, it has to be a chemical change. Iron filings separated from sand by using a magnet. This was the example we saw, although it wasn't sand, it was a different substance, but we saw this one. This one is physical. So you see these are two different things. Iron and sand are two different things. There's nothing common like sodium and sodium chlorides. The sodium is inside the name of the sodium chloride. So that kind of gives you the hint there. Fine crystals of silver chloride are separated from a suspension of the crystals in water. Okay, so it tells you that I have crystals, and those crystals are silver chloride, and I'm removing them from water. So crystals and water are two different substances, so this is also going to be physical. Okay, and I think that's all I have for that one. Nope, I have one more. I skipped C, don't ask me why. Copper is produced when zinc metal is placed in a solution of copper 2 sulfate. So, you see, copper is the same. Copper's in both of these. So that's going to make it what? Chemical. So that's how you can basically tell the difference. If I have the same name in both, it's typically going to be chemical. If I don't have the same name, it's going to be physical. Alright, one more problem for this video set. Indicate whether the following is a substance, a heterogeneous mixture, or a solution, which also means homogeneous mixture. Okay, milk. Now, don't think about milk when you bring it home from the grocery store. Think about milk after you forgot to throw it out and it's expired. Has anybody done that? It's gross, yes. But also, you'll see the fact that there's a almost transparent, which means you can see through it, layer at the top, and then you have this solid, icky, gross, smelly stuff at the bottom. Okay, because of that, it's just basically separated into its own two parts over time. So that means it is a heterogeneous mixture. Okay, bromine. Okay, we haven't gotten to the elements on the periodic table. That will actually be the next chapter, but this is an element on the periodic table, so therefore it is a substance. Gasoline. Okay, gasoline is, you might think one compound, but it's not. It's actually several different compounds that typically have 8 carbons in them. But you can't physically look at gasoline and see the different types of molecules. So therefore, this one is a solution. Okay. And aluminum. Again, I can find this on the periodic table. Since it's on the periodic table, it's an element, and therefore it is a substance. And so this is the end of the second part of this